Hi everyone, my name is Taehyuk Kim. I'm a fourth year PhD student at Carnegie Mellon. In this talk, I'm going to introduce our system called T, which enables to build state-intensive network functions on programmable switches. This is a joint work with my collaborators at Intel ByteDance and my advisors at CMU. To give you a context of this work, recently programmable switches have been gaining a lot of attention in both the industry and research community as a new way of deploying network functions. Since they provide predictable high performance at lower cost compared to traditional approaches, such as using standalone wheelbox devices or commodity servers, they become an attractive platform for various network functions. However, we observed that switch-based network functions cannot serve very demanding traffic workloads. An example of such demanding workloads would be a workload that consists of tens of millions of concurrent flows with a terabit per second traffic rate. Since a single programmable switch can process high traffic rate, it seems promising for such workload. Unfortunately, however, it cannot maintain necessary flow state for the large number of flows. And the key reason for this is limited SRAM space on the switch, which is tens of megabytes. Since SRAM is generally very expensive, just adding more SRAM cannot be a good solution. Instead, in this work, we try to tackle this problem by answering this question. Can we leverage larger and cheaper external DRAM that already exists near the switch ASICs? To answer this question, we developed Table Extension Architecture, or T, for programmable switches. We build on our observation that there's a bunch of DRAM available on commodity servers connected to the switch. By leveraging existing resources in the network in a flexible manner, T provides a scalable solution at a lower cost. At a high level, T provides a virtual table abstraction for network functions so that they can store a large lookup table to external DRAM and place a part of it on on-chip SRAM. While this idea of using external DRAM sounds simple, we have to address several challenges to realize this vision. Let me explain this with a simple packet processing example. Here, a packet comes into the switch, and the ASIC needs to look up an entry for a given key, such as byte-tuple of the packet, and process the packet with a retrieved key. In this example, it needs to look up an entry for a key 1. To achieve this, the ASIC first needs a capability of accessing external DRAM, which is normally not supported by the ASICs. In particular, since the access latency can affect the NF performance, we need to have a mechanism that provides low and predictable latency. Once the ASIC can access external DRAM, the next step is to locate and access correct table entry for a given key. This is challenging because while a table lookup must be done in a predictable manner, if a table lookup requires multiple DRAM accesses, it can result in unpredictable latency. So, to guarantee predictable lookup latency, we need to locate and retrieve a table entry in a single DRAM access. Along with this single DRAM access lookup, T must be able to defer packet processing, which means that during table lookups, it needs to somehow hold the packet so that after the lookup completes, it can use the retrieved table entry for processing that packet. And the key challenge here is how to defer only a packet corresponding to the lookup without stalling the entire pipeline or buffering at the switch, which can consume an excessive amount of switch resources. And the last challenge is about using multiple servers. While it is possible to achieve higher lookup throughput and better availability using multiple servers, there's a few challenges to utilize them effectively, including how to balance memory access loads across servers, and how to deal with servers' availability changes fast. We address these challenges with 4 key ideas. First, we leverage ASIC programmability to enable RDMA-based external DRAM access purely in the data plane. And we repurpose prior work called bounded linear proving, or BLP, to devise an efficient data structure called T-table that allows table lookups in a single round trip. Also, by offloading the table store to T-table, we enable asynchronous packet processing. Lastly, we employ small on-chip cache to support higher throughput and for better utilization of multiple servers. By combining these ideas, T offers a virtual table abstraction that provides NFs with an illusion of large lookup tables. To use T, developers implement their NFs with T API in P4, and then they can compile it with an unmodified P4 compiler, which gives them a binary. At runtime, T allows NFs to access lookup tables from either on-chip SRAM or external DRAM. We implement T API and runtime as modules in P4, and using the APIs, we implement canonical NFs, including NAT and stateful firewall. We evaluate T using a testbed consisting of a Tofino-based programmable switch and a number of servers with RDMA NICs. Now let me show you a few performance results of T. The first evaluation question is, does T provide low and predictable lookup latency? To answer this, we measure the lookup latency of T-enabled NAT with different packet sizes and compare it with server-to-server RDMA performance. Here, the x-axis is the packet size and y-axis is the lookup latency in microseconds. This result shows that T can achieve around 2 microseconds at median with low tail latency. Then how about lookup throughput? Here we measure the lookup throughput of T with a different number of servers and different flow size units, which can affect one-chip cache hit rate. Here x-axis is the number of DRAM servers and y-axis is the throughput in million lookups per second. We can see here that the throughput can be scaled by adding more servers. Also, we see that on-chip cache actually helps improve the throughput a lot. Now, let me close by answering a few frequently asked questions about T. The first question is, do we need specialized hardware to use T? Users need a Tofino-based programmable switch and some servers equipped with RDMA NICs without any hardware changes. In our testbed, we use NICs from Mellanox. And then next question is, can T support other applications beyond network functions? Basically, any applications using large key value lookup tables can benefit from T by offloading their tables to external DRAM. And does T affect other workloads on servers? Some memory-intensive workload can be affected, especially when the memory bandwidth is fully utilized. However, since T does not involve CPUs on servers during lookups, it does not affect CPU-intensive workloads on servers. Also, to avoid impacting other network traffic, T can be configured to use a portion of network bandwidth and prioritize other regular traffics. And what about the bandwidth overhead of using T? When a packet needs an external DRAM lookup, T generates one RDMA write and one RDMA read request for the lookup. This increases the bandwidth consumption of the switch pipeline for that particular packet without affecting the rest of packets. Another commonly asked question is why T does not use available DRAM on a switch. So there are two places where you can find available DRAM on a switch. The first one is in the switch control plane, where you can find a few gigabytes of DRAM. And there's another option, which is onboard off-chip DRAM, which provides some amount of DRAM as an extension of the ASIC. However, we found that both options suffer from limited access bandwidth and memory size because they are fixed at the hardware design time and it's hard to be scaled out. Also, the second option requires to add additional components to the chip, so it also increases an overall cost. So to conclude this talk, limited on-chip memory has been a roadblock for adopting switch-based network functions, especially for demanding workloads. To solve this problem, we built T that provides a virtual table abstraction for NFs, and we realize it with 4 key ideas. And our evaluation shows that it provides low and predictable lookup latency with scalable throughput for various network functions. With that, I'm happy to take any questions. Thank you.
Okay, thank you for a very nice talk. I see lots of questions on Slack already. And again, if you want, you can put them on Q&A. If you could unmute yourself, that'd be great for the Q&A. So there's actually a batch of questions from Hangzhu, who I believe is at Harvard, Praveen Kumar at Cornell, and Jackie Gao. Sorry, Jackie's at Harvard, and Hangzhu is at Johns Hopkins. And this is around the semantics of packet processing. Is it serializable, and also what's the semantics when you have updates to the offloaded state?
So I think that's a great question. So so for updates, I think here we are basically focused on the read-intensive network functions such as like NAT and load balancer and firewall. So the update rate is not that high, and basically the table insertion is done by the control plane, so that there's no like update related issue, and it's for those read-intensive network functions. And for serializability, I think it'll be better to like elaborate the question a little bit more.
Maybe so. What is the consistency guarantees if there's a sequence of packets that are accessing the DRAM state? What consistency guarantees, if any, do you get? Yeah, so as I said, it's a read-intensive network function. The network functions is our main target application. So serials of reads, requests does not affect the consistency of between packets. All right, so in the presence of writes, it's something like eventual or a weak form of consistency? Okay. Yeah. Okay, a couple of questions about the RDMA piece. So Gianni from Queen Mary asks, how do you generate the RDMA requests? Are you using the traffic generator inside a programmable switch? Yeah. And then I'll just bundle. Okay, go ahead, answer that one. Yeah, that's a good question. So, so since so in the RDMA over Ethernet or Rocky protocol, RDMA requests and responses are in just a Ethernet frame. So we can craft RDMA requests from the ASIC on demand by prepending RDMA headers to the original incoming packet. And it can also parse the response sent by the NIC. So yeah, just please refer to our paper for more details, and I'm also happy to discuss more on Slack. Basically, how it works is when the packet needs to look up a table, the ASIC prepends the RDMA headers on the original incoming packet to make it as the RDMA request. Okay. One more question, also starting with RDMA. So from Ben Pfaff at VMware, he's curious about the economic factors. So RDMA servers are expensive, especially if you need a lot of them, like 8 of them. So do you have an idea of kind of what kinds of applications this kind of widget would be useful for from a cost perspective? Cost perspective. So currently we are targeting deploying this T idea to NFV cluster, where there are already a bunch of servers, and probably like RDMA NICs are on those servers. But yeah, that's our current target. And more generally, currently, like many data centers are deploying RDMA NICs in their servers, so we can also deploy T on switches in such an compute cluster as well. Okay, I'll take one more question from Anna Cornfield Simpson at UW. For the RDMA read and write operations, the server side typically has to register memory regions and convey the virtual addresses to the client. So can you talk about how this setup between the servers and the switches are set up? And are there any instances where you'd need isolation? Yeah, so this the RDMA context setup is done by through the control channel between the switch control plane and the RDMA, the server, the daemon running on the server. So when you first initialize this T-enabled system, the switch control plane and the daemon and server will talk to with each other through, for example, some TCP out-of-band connection to set up those memory region and exchange the virtual memory address. And then it will populate the virtual memory address information to the data plane.
And at runtime, the data plane can use that information to locate and retrieve the correct table entry for a given key, such as 5 tuple.
Okay, thank you for your presentation. Very interesting talk. We have some questions for you. First of all, because now you have to look up the table from the server. So what is the typical latency between the switch and the server as compared to local lookup? Could you give us some hint about that?
Yeah, so for the latency overhead, when you access the external table on server's DRAM, it adds around like 2 microseconds per packet latency. So basically, from end-to-end perspective, your like end-to-end latency will increase about like 2 microseconds. Whereas like if you just do like a local lookup, it only typically it adds like some nanosecond latency.
Yeah. So do you think this latency is acceptable for some applications?
Yeah, because like if you consider some like a wide area scenario where the RPT is basically some like millisecond granularity, adding some like just a few microsecond latency would be acceptable.
Yeah, it's also related to my next question. So because now you have local cache, you also have the DRAM in the server. So how do you determine what kind of state should be offload to the server? So if the latency is an issue, so is it possible to say, okay, maybe some application, they are not so sensitive to latency, we can offload to the server. But if the application is more sensitive to latency, they can be kept in a local cache. So do you have any mechanism to determine how to offload the states?
Yeah, so that's a good question. And in the current design, we cache the frequently accessed entry on chip SRAM cache. So that, and also we observed that in typical traffic trace, or typical like a traffic workload, their like flow size is typically skewed, so that the majority of, the high volume of traffic can be like can be served by the SRAM cache. So that's
so in your paper,
yeah, there's specific like characteristics for like network function applications. But if you consider like other applications using T, then we may need to come up with a more sophisticated like caching mechanism other than just relying on this skewness of data.
And my other question is, in your paper, have you evaluated what's the cost if you want to migrate the table? For example, now you put A in cache, B in the server, but you want to switch the table. So what is it possible? Any additional cost? For example, do you need to recompile the switch, or is it possible to do that if you want to switch the table from the cache to the server and migrate the table from the server to the cache?
So your question is, can we change the cache entry or contents in the cache at runtime without recompiling the switch logic?
Yeah, maybe. Is it required recompiling or?
No, it can be done at runtime without recompiling or reconfiguring the switch logic.
So it's very expensive if you want to migrate the table.
So migrating the entire table may be very expensive because you need to insert those like large table entries, like tens of thousands of table entries in the like a switch and so on, vice versa. But
so this offloading decision should be done in the long-term granularity, right?
Yeah.
I see. Good. Let me see if I have other questions. Yeah, there is one question about, you mentioned DRAM at the switch. So based on your finding, would vendors now add memories to the switches, and how efficient would be, and any difficulty we may face? For the vendors, do you see any vendors they planning to add more memories in the local switch?
So the example I used in the last slide, the one slide before the conclusion slide, we find, we know, we are aware of one switch vendor, chip vendor, which provide like that extension, ASIC extension DRAM. But from our understanding, that's usage is very limited. And also, what was the question? I think, yeah, I think that's the only case we are aware of currently.
Okay. And let's do one more question, final one. So yeah, someone asking, can we extend T to realize a big shared memory pool using SRAM of all the switches? Basically, they're asking whether the switches, multiple switches can share their memory instead of using some external server.
Yeah, yeah, that's very interesting direction, I guess. Yeah, I think we can also extend that this asynchronous lookup idea or asynchronous packet processing idea to use the SRAM on other switches. So, but I guess there are other like additional challenges we need to address.
Okay.